Okay, welcome back. In this video, we're looking at angular velocity. So let's review some user relationships from video one. In video one, we talked about circular motion. We talked about an object moving in circular motion having a linear speed, the speed at which it moves as it rotates around in that circular path. We talked about that as being the change in displacement over time, which for a full rotation would be 2 pi r over t, or the circumference over the period. We also introduced the radian and reviewed how do we figure out angles in radians, because that's our standard unit when it comes to rotational and circular motion. And we saw that 2 pi radians is 360 degrees, and that the radian is the ratio of arc length to radius. And this is useful because we use polar coordinates or defining angular or defining the position of something moving in a circular path in terms of its radius and its angle. We find that more useful than xy coordinates. So let's look at a couple new things. And we're going to look at angular displacement and angular velocity. So if we think of, let's take this to be our ball again, moving in a circular path. And it starts at some point in time, at some angle, and then moves through a change in angle from theta initial to theta final. We're going to define its angular displacement as its change in angle, which is just theta final minus theta initial. Again, this is going to be in radians as our standard unit. So if we start talking about how fast is the angle changing, now instead of looking at the speed of the object at the end of the string in this case, we want to look at what's the rate of change of the angle. So if we think about angular velocity, which we're going to define with the symbol variable omega, which is lowercase omega. Omega is the rate at which the angle changes over time, just like standard velocity is the rate at which your position changes over time. We're just now defining position in terms of angle. So sometimes we see this omega bar, sometimes you see it omega average, but it is a change in theta over time. Our standard units for that are going to be theta in radians, time in seconds. Now you often will see angular velocity given in terms of degrees per second, revolutions per second, sometimes revolutions per minute. So these are all different units that when we're solving problems, we want to convert back to our standard units, which is the radian per second. So that's angular velocity. Well, now how does this relate to the speed at which the object's traveling, the tangential speed or the linear speed of that rotating object? So let's take what we knew from the first video, and that is my average linear speed was my change in arc length over time, or how far does it travel, and it's traveling along that arc length, so delta S over delta T. Well, we also know from the first video that the radius times the angle that it's changed equals the arc length. So if I start at 0 and go some angle, it's S and R, but I could also write this as the change in arc length is R times the change in angle. So if I look at how quick my arc length is changing as a rate over time and divide both sides by delta t, what I see is I'm left with delta S over t, which is just my linear speed, is equal to R, and then here I have my angular velocity. So the linear motion of an object moving in circular motion is related to its angular velocity in terms of R times omega. So that's going to be another useful equation that we're going to use often. So one last thing we'll say in this video is what if my angular velocity is constant? Okay, so when omega is constant, we're going to look at problems just like we looked at constant speed or constant velocity problems first. When omega is constant, we have what's called uniform circular motion. The uniform referring to the idea that the rate of change of the angle over time is constant. This would tell me if this is constant and the radiant doesn't change, that my speed at any given point in time around the circle is constant. And so when we see or hear uniform circular motion, just know that speed is constant and that angular velocity is constant. In this case, the one term we haven't thrown out there yet that I can throw out now, alpha, which is going to be our angular acceleration. When we have uniform circular motion in UCM, alpha is 0. So this first batch of problems in this first unit, we're dealing with constant angular velocity. So our omega, or our alpha, excuse me, is going to be 0. And that's rads per second squared. Okay, there you go for angular velocity.